In previous video, we talked about moments of a charge distribution. Here, we are going to extend our discussion on this topic. Last, we saw potential on a point A due to some charge distribution rho can be represented in this form of power series. This power series is called multipole expansion. It's called multipole expansion. In this video, we are going to explain these terms K0, K1, K2 and so on. Here K0, this is called monopole moment. Called monopole moment. Here K0 is nothing but simply total charge in a distribution. Distribution. If equal amount of positive and negative charges are there, then this term is going to be 0. For example, as we see in a singly ionized molecule, if this is our molecule singly ionized, then K0 here will be equal to E. So if we have K0 is equal to 0, then we move to our next term K1, which is called a dipole moment. For example, in this system we can see in this here plus 3e charge here and minus 3e charge in this sphere. So here total charge of this system is 0, but in this example we'll still have some dipole moment. It is dipole moment. Dipole moment, it simply tells us about the relative displacement of positive and negative charge in the direction towards A. Now here if we see r prime cos theta is simply z prime, as we have seen in our previous video. In charge distribution, our point some r prime here, so this angle was theta. This distance is simply r prime cos theta. This is at x, y, if I denote these. Here one thing to note is if KO is 0, then K1 is independent of choice of origin. We can prove it. Let's do it. Here, okay, let's start again. If I replace z prime by z prime plus z naught, then if I insert it in integral r prime cos theta dv prime do rho, it will, and this was our z prime, then z prime plus z naught into rho dv prime. It implies z prime rho dv plus z naught rho dv. Here this is simply a constant, and we have chosen K0 is equal to 0, so this doesn't contribute, hence we get it same, that is K1 is independent of choice of origin. If our this term K1 is also 0, then we move to next term, which is K2. It is called the quadrupole moment. Called quadrupole moment. This quadrupole moment, it is a tensor quantity. A tensor quantity, and also our k1 was it is a vector quantity. And let us talk about how potential and fields vary due to these moments. Now we will see the variation of potential and fields. If k0 is non-zero, then potential will vary as 1 over r, and field, electric field, will vary as 1 over r square. If k0 is 0 and k1 is non-zero, then this implies potential will vary as 1 upon r square and field will vary as 1 upon r cube. And similarly, if k0 and k1 are both 0, then implies, and k2 is not 0, then it implies phi a will vary as 1 upon r cube, means potential will vary as 1 upon r cube and field will vary as 1 upon r to the power 4. An important point to note here is that if k0 is non-zero, then no matter how large k1, k2 and so on may be, if we go out to sufficiently large distances, the k0 by r term will win out. That is, potential will depend only on 1 upon r, not on 1 upon r square and 1 upon r cube or anything else. If you have any doubt, please let me know in the comments.